So, Pratham, picture a room where down doesn't point to the floor like normal.
Hmm.
Instead, it points to one of the walls.
Yeah.
So, everything you thought about up and down is suddenly sideways. It's all 90 degrees translated, you can say.
So, so if I was standing there, my feet would touch a surface that looked like a wall, but my brain would think it's the floor. It sounds a little
Yep.
disorienting, right?
Precisely. It is going to be very disorienting, especially if it's your first time walking on a sideways wall.
Yeah.
And as you start walking forward, because you see a cookie over there and you want to go get it, your body tries to adjust like the floor is where it expects. But really, since the floor is angled completely
Hmm.
differently, each step will feel strange. So, yeah, you will be pretty disoriented.
Yeah, so my sense of balance is constantly being tricked, and I have to consciously figure out where I have to put my feet, right?
Yep. And your instincts about gravity will be challenged constantly. You'll start leaning in ways that feel wrong, but they're necessary to avoid falling. That's what your brain will think, even though you're actually walking on a straight path to get your cookie.
Okay, I guess maybe the easiest way to imagine it is like spinning the whole room so that this force called centrifugal force is basically pulling me towards a wall, which acts as the floor that I walk on. Okay. So
Yeah,
basically, when we go in a circular path, if you suppose spin a ball on a string around a circular path like this, what you'll find is that there is a force that goes towards the center of the circular path, which is in the
that's a centripetal force.
tension of the string. Yeah, it's called the
Yeah.
centripetal force. And opposite to that is another force which is apparent. We call it a pseudo force. It doesn't really exist, but we've just made it so that we can have that, you know, Newton's
It's
third
for
law of
explanation
energy.
purposes.
Yeah, we have that Newton's third law of energy, right? Every action has an equal and opposite reaction, where basically we are trying to map this as the reaction force. So centrifugal force in this case is somewhat like a reaction force. So it pushes us outwards, basically at the boundary of the wall that we are spinning the room on. That is
So
what
that's why
is
you stay
centrifugal force for
towards
us.
on the wall, right?
Yeah, so that is why we feel like that is the floor. The wall is the floor that we walk on.
That's the apparent pull that you feel towards the wall,
Yeah,
right? And that's
yeah.
the idea. And engineers argue endlessly on how to make this work in practice. Whether it's better to have small, fast spinning pods for a personal gravity effect, or enormous, slowly rotating wheels where gravity builds eventually. Like, basically, I think the entire ship spins, or everyone has their own spinning pods which they roam around in inside a spaceship, I guess.
I mean, tiny pods would be intense and fast, but I guess a giant wheel feels more like a real environment, right? It would
True.
let you walk naturally without you or your body constantly panicking or in a state of fear.
I mean, either way, you end up in a place where your mind is always recalculating which direction is truly down,
Mm.
and every moment is a subtle negotiation between instinct and physics. Wise words. It's
Yeah,
it's it's difficult unless you get used to it. Up till the point that you get used to it, right?
yeah, hats off to our astronauts. I can imagine someone trying to run there, and it would feel like you're playing a trick on your own body and constantly questioning what is upright, what is down, what is sideways, because it's all changing every instant, right?
Exactly. And now, since we spoke about centripetal and centrifugal forces, now we're not going to introduce any equations about them. Let's just go a bit more on the simpler side, shall we?
Yeah,
So
sure.
let's think of a playground roundabout, okay? As it spins, you feel that you're pushed outward. Okay, you can try this. Like
Yeah.
if you wanna have a real physical experiment for fun with your friends, you'll feel pushed outward, and this force will only increase the faster it spins. And that push that you feel that can stand in for gravity because the push is outward. And then if you have walls on the roundabout, like which obviously you don't, but in the spaceship you will, that wall is actually your floor. It's reminiscent of the wall that we were speaking about in the starting of the episode. That wall is just the floor 90 degrees turned. So it's the new floor. And that's the basic idea behind artificial gravity. It's not actual gravity, it's just circular motion. That's it.
Yeah, and if you're feeling adventurous, maybe you can try and jump out of the rotating merry-go-round or whatever you want to call it, and you can
Yeah,
see
be very careful.
where the force takes you. But yeah, we don't endorse that
we're not
specifically,
recommending it.
and
We're not.
we are not liable for any injuries that you might have. Just saying. But yeah, you can definitely try it out if you want. And also, some quick relationships to keep in mind are that the stronger the spin of the merry-go-round or whatever the room that you have, the stronger is the push that you feel. And
Yeah,
the bigger the radius of the rotating platform or the room, the less spin you need to feel that same push. Okay. So radius and spin rates are inversely related for something like a gravity-like feeling. Basically,
true.
uh, like Arnav said, we won't go into the equations, but if we can just tell you an equation, that would be a little bit more,
Yeah, go ahead.
better to explain. So basically, acceleration, the push that you feel is equal to omega squared into the radius. Omega is your
Angular
uh,
velocity
angular velocity or basically the spin that is there. That's it. So the
is
more
just measured in being.
you increase both, the stronger push that you feel. That's it.
Yeah, basically, small radius equals to fast spin,
Yeah.
and fast spin equals to weird everyday surprises. Like, for example, if you walk towards the center, things will curve. If you turn your head too quick, your inner ear will complain. That's the Coriolis effect. It's not a monster term, it's just the sideways nudge that you'll feel when you move inside a spinning frame. It's like you're battling against the gravity. It's like walking against the tide, kind of. It's kind of like the Coriolis effect where whatever action you want to do, whatever motion you want to perform, it just opposes it with an equal, or like it opposes it with some sort of motion
Hmm.
in the opposite direction necessarily.
Yeah. Yeah. And for maybe an example, you can imagine like a compact exercise module where the radius is about as long as a small car. To
Okay.
feel close to Earth gravity, it needs to spin very fast, like very noticeably quickly, right? And that gives a very strong outward push at your feet, but your head will feel like quite noticeably lighter than your toes. And simple tasks like pouring a drink of water or something like that will get really awkward for you. That's what your astronauts basically feel when they are in a space shuttle.
Exactly. So the example that Pratham just gave is basically small radius with it requires a faster spin. On the other hand, if you contrast that with a giant wheel, like a Ferris wheel, let's say,
Hmm.
it's like a city block scale Ferris wheel. Okay, like it's huge. It's not like a usual Ferris wheel. It's like the world's largest Ferris wheel. Okay,
Yeah.
but it barely spins each minute. Its angular velocity is so low, so walking around it feels relatively normal. But the thing is, if you want to take that Ferris wheel city block size into space, that is a small engineering problem. It's just a small problem that is really difficult to overcome, basically.
Small problem that's difficult to overcome. I like your
Yeah.
choice of words. Yeah, but maybe if you want some intuition, uh, you can see that for comfort, for most people, like families, kitchens, daily life, whatever you think about that is going on in your home right now, you would tend towards a larger radius and a slower spin. Probably because, as Arnav said, you can like walk around on it, right? It's better for you.
Yeah.
Okay, but
Relatively.
if
Yeah.
you just want maybe like some prophylactic medical therapy or something like that, a short spin session to fight bone loss, maybe something like that, a smaller, fast centrifuge might be better for you. That's basically what
And
research has found out.
that's true. That's true. Basically, to summarize, spin gives you gravity like force,
Hmm.
and smaller radii need faster spins to create the same amount of
Yeah.
pushing artificial gravity effect as larger radii with smaller spins, like to equate that basically.
Yeah.
And it does create weird motion cues. The another con of these bigger circles or these bigger, I would say, donuts, you can say, donut spaceships or spherical or whatever. Point is, if they're bigger, the radii are bigger, they're gentler on the humans, but they're very, like, significantly more difficult to build, right? And
Yeah.
especially to take into
Yeah.
space.
Yeah, and if we talk bodies, like microgravity does some real damage to you. Like it's a
Hmm.
medical term, but it causes muscle atrophy, which is basically muscle degeneration. And in addition to that, you have bone loss or fluid shifts in your body as well because your gravity is constantly shifting. Okay. So your brain is basically tuned to think that because your gravity is shifting, it will shift the fluid in your body as well because it's controlling everything, right? And
Right.
because of that, artificial gravity could help some bit. Okay. But human tolerance isn't just a yes or a no, right? It's not binary. It's often a spectrum that we observe, and it's basically about how people respond to certain types of rotation over days or even months for that matter.
Yeah, because every human responds differently to everything. Because that's what makes everyone unique. We respond to different stimuli differently.
Yeah,
So another thing is, as we spoke about earlier, inner ears,
yeah.
and basically how if you walk towards it, your inner ears might complain, right? Basically, your inner ears are tuned to Earth's stable gravity of
Mm,
G equal to 9.81 meters per second square, right? That's what we are all familiar with. Some people
yeah,
round it off to 10 in physics problems to make calculation simpler, or they use 9.8. But yeah, that stable gravity is what our inner ears love and would love to stick with. But in a rotating habitat, like a rotating huge spaceship or your roundabout, the head turns and your quick movements, like if you turn around your head really quickly, they produce Coriolis deflections that can cause disorientation, nausea, and long-term adaptation issues. Some people like just adapt faster just because of their genetics or other reasons. Others may struggle. Habitability is not purely a physics equation, it's more bio and more physiologically negotiated with each person's body. It's up to each person's health and genetics and conditions, right? It's not up to the person themselves directly.
yeah. And you can really imagine this if you have vertigo or if you have someone if you've observed someone who is having vertigo. Vertigo is basically an inner ear condition that makes you cause a fear of heights when you go up to a substantial height and then you feel dizzy and you feel nauseatic. This is
Right.
somewhat similar to what you feel when you are basically in that vertigo state. Okay. Just for real world purposes if you
Context.
want
Yeah.
to like relate to it. But if you're thinking about the design point of view, like how we can mitigate this, it is of course by reducing the spin rate and increasing the radius, right? Or it can also be how to limit how much people move radially. Of course, like every physics problem, there are trade-offs everywhere. Bigger radius would mean more structure and more mass. So, and slower spin reduces those vestibular problems in your ear, right? But it costs you a lot more in construction. And of course, as we might have discussed in the last episode also, if you're moving through space and you want to get somewhere fast, ideally you should need as less mass as you would like, right?
Yeah. Because moving more mass is simply just harder.
Yeah, exactly.
It takes more energy, equal to mc squared. You need more energy to move that much mass. It's directly proportional.
Now E is equal to mc squared
As
is
he
to
da-
convert mass to energy.
yeah.
F is
Yeah, so
equal to ma. You need more
no,
force to accelerate a mass
that's
to
true.
the same
No,
object,
but
same
both ways.
acceleration.
Yeah, both ways. So another thing, come back to the point, let's not digress too much.
Yeah, we won't digress.
You said, yeah, you said construction, right?
Yeah,
So if you have bigger
costs.
disks, like we've spoken about so much earlier, structural engineering adds another constraint, right? Because you can't build that big structures, and the
Yeah,
fastest the structure spins, the more stress is there on the structure, and there are more forces that try to pull the structure itself apart because the forces that we're talking about, they act on the structure itself. So the structure itself has outward forces that might cause it to literally just break apart and move outward or break it outward into like many pieces, right? So even if a small centrifuge is appealing for cost and compactness, it does still need strong materials and careful balancing. And even if you want a big one, then you'll probably need like tethers, wheels, rotating modules. and each of them have different failure modes and maintenance demands.
Yeah, and in addition to this, there's also docking, right? How do you move between a non-rotating ship and a rotating habitat? Either you have transfer nodes that slowly rotate, or you maybe match rotation and add both mechanical complexity and risk.
Yeah, I think this was there in Interstellar where they tried to dock while it was rotating, or was it Fantastic Four? I can't remember, but there's some movie out there where someone's trying to dock in a spaceship that's rotating, and they have to match very carefully the angular momentum, the angular velocity, like the rotation of the rotating spaceship, so that they can dock very carefully while that's rotating. It's matching the rotation and it's going closer as well
Yeah,
so that it can literally dock, right? So another complexity is literally daily life, right? Plumbing, cooking, moving food between
plumbing,
floors.
plumbing. Arnav,
Yeah, you know,
trying to go to the toilet when your gravity is constantly changing. Like the direction of it is constantly
exactly.
changing.
Exactly. So everything matters, right? People need to live their lives on the spaceship. If you want to go for interstellar travel, if Elon Musk wants to achieve his dreams, he needs to figure out the problem of artificial gravity, right? Probably. If he wants to send people out in without vestibular problems, right? So gravity gradient, basically the difference in gravity on across the floors of the donut-shaped spaceship or the circular disc spaceship, the gradient matters. The difference in the
Mhm.
gravity across the floors matters. Like in small radius habitats, like head to toe gravity difference is noticeable. In large ones, it's negligible. So the bigger it is, the better. Like
Mm.
designing kitchens, bathrooms, as you said, bathrooms, and
Yeah,
stairways, for example, for rotating environments, changes how you build everything because everything is different for you. You don't have one common source of gravity. You have to adjust for different. If this is our spaceship, the outer ring of it feels the most push, most outward push, and as you go closer to the center, the gravity, the force of the apparent gravity gets lesser and lesser because you're going towards the center. So that descent, the gradient, the reduction in the gravity, the difference in that, that has to be accounted for. It basically gets harder and harder for you to
yeah,
have that gravity in the center of the spaceship, and that's why we are saying it like a disc or a donut, because there's no point in having anything in the middle if you want gravity in the middle. Otherwise you can just keep it like a storage space, I guess. I don't know, not really a big of an issue to just store stuff in anti-gravity, like in no gravity in the middle of the spaceship,
mm.
storage.
Yeah. But after all this discussion, basically the bottom line is that your health would prefer gentle spin and longer radius, but engineering and cost effectiveness would prefer something that is compact and has a lower mass, right? And where you kind of negotiate is the sweet spot, is somewhere in the middle. Of course, it's a spectrum, but it's somewhere in the middle. And
Yeah, like,
depends on your mission's goal, whether you want to go to the moon or you want to go to Venus or wherever it is, your goals are. It depends a lot on that as well. And of course, it's somewhat of a medicine countermeasure versus a permanent colony. Just what you want in the future.
okay. So as we've been speaking about throughout the entire episode,
Hmm.
let's walk through specifically the two archetypes, the short radius modules and the long structure habitats. Okay,
Okay.
let's like delve deeper into them.
So basically, your short radius modules are like high-tech treadmills, or you can call them exercise pods. Okay. So they're compact, cheaper to launch, and they are usable as countermeasures. You spin people for an hour a day to reduce the bone loss, okay, or to reduce the
Yeah.
underlying conditions that we discussed about. And they are practical for current missions because you can test them somewhat relatively cheaply on Earth as well, or even in lower.
Now, as I said earlier, everything has pros and cons, right? Now, the
Of course.
downsides, as we've also spoken about some of them, but since we're delving deeper, is discomfort for everyday living, the strong
Yeah.
Coriolis effect on common motions, like the vestibular issues on the inner ear, etc., and complex docking if you want people to live inside full time.
Hmm.
It's great for medical use, questionable for family-sized living spaces, because it's difficult to interact, right? Then.
Yeah. And if you look on the flip side, your long structure habitats are the classic space wheel idea that we discussed about.
The space
Low
donut
spin,
sounds cooler.
huh?
Space donut sounds cooler.
Okay. Space donut idea that we discussed
Yeah.
about earlier. So you have slow spin, big radius, and a more comfortable gravity and gravity descent. Is that what you call it?
No, gravity
Gradient.
differential. Gradient.
Differential. Okay. So
Both
you
ways,
can
both.
with that big structure, you can have space gardens, kitchens, maybe even sports without weird sideways movements. It's just whatever your
Yeah, you can play some
imagination is
basketball.
limited.
Yeah. So another thing is the con again, as everything has, the price tag. It's huge. You need massive structures. You need to assemble it in orbit or in situ resource to keep the mass down. Because even if you use, let's say, carbon fiber, which is really strong but
Hmm.
and really lightweight, right? Point is, it's expensive, and you need to have countermeasures for the countermeasures because the structure itself is experiencing large amounts of force, and the structure itself needs to sustain its own mass on top of the mass of the residents or the occupants and their many belongings, right? If you're going
Yeah.
for a long distance mission, it needs a lot of stuff. So you need reliable horizontal and rotational, and basically you need a lot of stabilization, and you need stairways to get on and off the wheel, because if it's rotating, then how will you dock with it very easily? It's possible, but it's hard.
Yeah. And because we've discussed both of these options now, I feel that there's a need to mention that there is a hybrid idea, right? It's called tethered systems. Basically, it's two masses connected by a long tether spun around their center. Okay, basically, you
Okay.
get large effective radius for less rigid structure work. Okay, but of course, like Arnav said, everything has its own pros and cons. Tethers also have their own problems. Okay. There are often micrometeoroids strikes on the tether, basically like very small meteors or asteroids that really hit the tether
Because they're
and
so large in number, there's a high probability
yeah,
for any of them hitting the tether. And even if one of them hits the tether, that compromises the safety and the functionality of the whole
yeah, and it
machine.
damages the tether basically.
Exactly.
So
And after a point, it's just going to break. And even if it
yeah,
doesn't break, it's just going to slow down because of the impacts.
yeah, and what this tether system also creates is basically your long-term material creep, which is not very good. So if you want to use this system for like an extremely long term, say you're traveling to Pluto from here, okay, the idea may not work. Okay, it may,
Yeah.
but it may
Pluto's
not. It is
episode.
expanding at a rate that is
It is faster than the speed of light. Exactly.
you can't do it.
So that's why Pluto is still of a more out of reach mission as of now. Still,
Even Mars looks like out of
even
reach.
Mars
At
is
least
exactly,
is the furthest that we have gone physically. Okay.
exactly.
The last part about this tether system is that it also has very complex dynamics. Okay. They're so complex that they're even hard for NASA engineers to comprehend. Okay. So it's not complex just for us, but it's also a little complex for them.
It's
Understanding,
harder than rocket science.
understand this is rocket science, Arnav.
This is harder than rocket science. This is you're building the spaceship beyond the rocket. The rocket just takes the spaceship to orbit.
Yeah.
This one is how to assemble it in orbit. This is harder.
Okay.
Step two.
Yeah, and practically your near-term missions will probably mix a lot of these approaches. So they may mix short radius centrifuges that are for health and experiments, and research into scalable long radius, what are they called? Habitats. Sorry, long radius concepts for your future habitats. So they may mix both of these approaches just to make sure that we have all the data that we need to go ahead.
Yeah. So you can think of it like incrementalism, right? You prove
Yeah,
the medical benefit, then you justify the structural investment for a larger habitat so that it's a win-win situation, right? So you have both safety and
yeah.
like people are happy that they're not dying due to their
Wow.
bone loss or their inner ear vestibular issues, etc. But they are also happy in terms of they have like as you said, they're supposed to play. We can play some basketball on the spaceship, So people have something to do. They don't have to do the rocket science of all the experiments on space.
Yeah,
It's still like that.
yeah.
So from here, where else can we go? First, we
Mm.
can test small systems multiple times, many iterations. Ground
Okay.
centrifuges tell you a lot, like how people would adapt, what protocols would help, and what spin prescriptions reduce physiological loss. Basically, as we said earlier, different humans respond differently to different things. Basically, you just test that out and get an average or like a somewhat of correspondence to get
Somewhat that
relationship, exactly
you
correlation versus
can,
causation, so that you can plot it and figure out to like make it you get something useful,
yeah,
if
make
data
it ideal for what your
everyone
goals are and what
exactly
type of people you're also trying to send to that
exactly
goal. All of this data is collected. You put compact centrifuges in orbit, actually. So maybe inside space stations or just for free flying. And you test real microgravity using real people in
no you use fake people.
short duration artificial gravity sessions. Okay. So once you've done that, you can, start to build on that as well. And the ISS has hosted some of these centrifuge experiments as well, and they are starting to get more consistent. But again, long-term data is still the missing piece. We just have one ISS. Okay, so you can't conduct loads of
Soon to be
experiments.
replaced, right?
Yeah, yeah, yeah.
Yeah,
Like
so that's
I,
at least good. Also, by the way,
next to
ISS
next
is the
year.
International Space Station. Just
Oh
if
yeah,
anyone was wondering. Okay, so after that we can try tether demonstrations. Like small satellites can spin with a tether to test dynamics and retrieval. That also informs whether tethers are robust enough for bigger structures. So if you try tethers on a smaller scale, then you can slowly scale it up, and then you can try it on bigger scales to check without spending all that much money directly on the big one. You first prototype, right? That's what
yeah.
experimentation is about. That's what science is about. Testing your theories and then making theories, testing your predictions, and then actually
Deploying it real world.
deploying it. Exactly.
And parallel to all of this testing that you're doing, you also need to do some materials and manufacturing research. If we can
Oof.
build tighter, lighter, and also stronger components in space, or if we use something like asteroid material,
I mean,
the
asteroid material is
economics,
still going to be elements that we can find on the planet Earth. So
yeah,
it's going to be, it's going to
the economics of the big wheels improves fast. If you
be true.
can do something like this, the big wheels that we talked about, basically.
Yeah. Yeah. The big donut spaceships.
Yeah,
So,
don't.
yeah. So, another issue, as with always with physics, there are just issues and issues. There are more questions than answers. The interface problem, transferring nodes and docking for rotating habitats, as we've spoken about. Now,
Yeah.
prototyping safe, repeatable methods to move people and cargo between rotating and not rotating sections is basically as important as the human physiology tests, right? Because if the people are fine, but when they're transferring from one place to another, that's really unsafe or basically impossible, then what's the point? They just
Yeah,
stranded in
it's
whichever
a whole
side.
failure. It's a big failure.
Exactly.
Yeah,
Everything's
so
important.
yeah, the roadmap is it's basically practical and in theory incremental as well, right? You start to
Scalable, yeah.
increase the scale of everything that you're doing. That is basically it. So you start from ground tests, you go to in orbit short radius trials, Then, as Arnav said, you have to try those tethered demos. And after that, you have to move on to scalable manufacturing. That is even economical for you. And then after you've done all this, then you have to do long radius habitats when your data, materials, and systems all improve and they line up together such that you can actually make this a reality.
So basically, artificial gravity, it's not like a single engineering decision where you can just flip a switch and turn it on
Hmm.
or off. It's not that easy, right? As with
Yeah,
everything
it's
in
constant
physics.
trial and error.
It's exactly, it takes a lot of time to implement. It's a chain of trade-offs. Human tolerance versus structural mass, what the mission goals are, everything has to be taken into account. And humanity will likely start with small targeted uses and only scale up if the science and economics make sense. Because if the science doesn't make sense, then it's not possible. And if the economics doesn't make sense, then also it's not possible because no one's going to spend money on it if they don't have the money to spend on it. So it's an engineering negotiation with human bodies at stake.
Yeah,
Everything has to be taken into account.
yeah. This spin gives you somewhat of a way to bring back normalcy to space life, but it asks for new thinking about architecture, movement, and your daily living. So basically, if you want to keep it short and clear, you need small spins for therapy, big donuts for comfort, and a lot
Yes.
of testing in between those phases.
Yeah. That is the map. That's groundwork. Now the hard part, funding, materials, and a lot of patience.
Yeah, this is the classic. Okay, if I'm spending money on this, where does this lead to kind of dilemma, right? A lot of people or a lot of lawmakers are not willing to spend money on space exploration because it's not creating a lot of immediate benefit for us. That's
Correct.
why
Correct. It's a
we
long
see
term thing
that
rather than a short term thing.
even our country's own space organization is not extremely well funded. At least the US can be thankful that NASA has substantially more funding, doesn't have a
ISRO
lot of
has
funding.
launched the Chandrayaan rocket with the budget for the actual launch of the rocket was lesser than the making of the movie Martian or something like that.
Exactly,
So
exactly my point.
yeah,
So
so they're really under a really low budget, but they're doing stuff.
yeah,
And that's
and
exciting.
that is what is attracting us towards this space as well.